Okay. So what is identity matrix means? As we have discussed earlier, the diagonal matrix, the diagonal elements will be one. Other than diagonal elements will be zero. And the matrix multiplication, any matrix multiplication with identity matrix is nothing but A into I will be A, or I into A will be A. So this is the property of the identity matrix, where if you are multiplying if any matrix with identity matrix, will get the same result of as that of the previous matrix. So to find inverse by using elementary row transformation, we have inverse. What like we have seen here, we need if you need any inverse of any matrix, then with the help of identity matrix, we can go for calculation of inverse of A. Like if you wanted to find like inverse of A, then we can do like this. Right, A is equal to I into A. So both are same. Apply various row operations on left hand side and apply same operations to I on the right side, but not A on right side. So step 3. From step 2, we get a new matrix equation. We will see this with the example. Actually, we have like a for transforming, for getting any A inverse of any matrix, we can go for elementary row operations and elementary column operations. So here this represents inverse order 2. We have taken a matrix of order 2, and we are finding out the inverse of that matrix like 6, 5, and 5, 4. So we can go for A is equal to I into A, 6, 5, 5, 4 is equal to 1, 0, 0, 1 into A. So we'll apply some of the operations on rows. So that's why it is called as elementary row transformations or elementary row operations. So R1 is equal to R1 minus R2. What we are doing means, we are taking the row 1 to the left side, and to the right side in identity matrix, we take the row 1 and we'll do the operation is R1 minus R2. So 1, 1, 1 and 5, 4. Actually, previously we have like 6, 5. Now we have got 1, 1. How we have got this means, we have R1 we have did a operation that is R1 minus R2. 6 minus 5 and 5 minus 4. 6 minus 5 is 1 and 5 minus 4 is 1. So that's how we'll get. And here in identity matrix, 1 minus 0 is nothing but 1, and 0 minus 1 is minus 1. So we'll go like this, and finally we'll get like this. A inverse. After here, the main agenda of left side is we need to get here identity matrix. Then after getting identity matrix here, whatever the matrix here it is there, we can get this to this side, and it will become A inverse. And any matrix multiplication with identity matrix is the same matrix as we have learned earlier. So A inverse is equal to minus 4, 5, 5 minus 6. So this is the A inverse matrix, that is minus 4, 5 and 5 and minus 6 represents the inverse of A. So next we have like inverse of order 3 matrix. So using elementary row transformation, like we can this is nothing but a third order matrix where we are doing some row operations for finding out the inverse of A. Similarly, like R1 is equal to 3 R1. These are not mandatory that R1 is 3 R1. You need to go for iterations, different iterations, and it's on your own wish. You need to get that left hand side identity matrix. Then we can bring it this A to this side. Then it will become A inverse, and whatever the matrix to the right hand side it is there, that is the inverse of A. The same thing here also we have done. Like we have got here third order identity matrix. Then here we have got matrix. This is the inverse of A. So we have like if A has an inverse, then A is said to be invertible. And if any matrix, if it is not having A inverse, then that matrix is called a singular matrix. So if it has got A inverse, then it is said to be invertible. If it has not got any inverse matrix, then it is called a singular matrix. So here the determinant is scalar. So here the next concept in this matrix operations is determinant. So your determinant is nothing but I will show you for 2 by 2 matrix. It will be easy. Oh, we don't have here. Okay. In eigenvalues, I will show you what is determinant. So let me show you here also. Here, like determinant is a scalar value of a matrix. So here A two pipe operators represents here like A11 represents this determinant of A. So here we'll take A11. So we'll leave this column and this row, and we'll select this matrix where we'll do A22 into A33 minus A23 into A32. So that is A11 into A22, A33 minus A32 and minus A12. Next we have selected this A12, A2. So we need to, we should not take this first row and second column. So whatever the remaining elements are like A21, A31, A23 and A33, we need to take them and multiply it with like A12 into A21 into A33 minus A31 into A23 plus A13 into A21, A32 minus A31, A22. So this is nothing but determinant of A, and it will not be equal to 0. So then inverse of matrix exists, then A inverse. So if inverse of if it is not equal to 0, then inverse of matrix exists. Otherwise, A inverse will not be there. So if it is determinant of any matrix is equal to 0, then A inverse will not exist. So this is regarding some of the matrix. So what are the key points in this means? A matrix is an ordered rectangular array of numbers or functions. A matrix having m rows and n columns is called as order m by n. So these are all the things we have seen. Okay, these are also this is something like cheat sheet for matrix operation. Next we'll move on to the next topic, that is eigenvalues and eigenvectors. So here comes the eigenvalues and eigenvectors PPT. Let me share this. So we have like eigenvalues and eigenvectors. So as earlier we have discussed, like for finding for doing any principal component analysis or SPD, we need to know vectors, matrices, and eigenvalues and eigenvectors. Like for finding a covariance matrix, then with the help of these things, we can go for principal component analysis and SVD, a singular value decomposition. So here, pre-definition workup, that is not important. So let me tell you what is eigenvalues and eigenvectors. So let A be any nth order matrix, and x bar is a non-zero. What does x bar represent? It represents a vector. X bar means nothing but vector. Here A represents matrix, x bar represents a vector, a non-zero vector, which is having n by 1 column, and lambda is a scalar. So if A x bar is equal to lambda x bar, then here x bar represents the eigenvector of A, and lambda represents the eigenvalue of A. So how we are converting this A into, we are multiplying a matrix with a vector and a scalar with a vector. So whenever these two are equal, then we can say that lambda is an eigenvalue and x bar is a eigenvector. So how we can find means, given a matrix A, x is an eigenvector and lambda is a corresponding eigenvalue if Ax is equal to lambda x. A must be square and the determinant of a minus lambda I must be equal to 0. So how means when we are taking this lambda x to the left hand side, we will get a x minus lambda x is equal to 0. If a minus lambda I into x is equal to 0, like a minus lambda I uh, will it should be 0 and this x should not be equal to 0. So that's why we are calling it as trivial solution is if x is equal to 0. If x is equal to 0, we will move to nothing. So if x is equal to 0, then we will not get any eigenvalue or eigenvector from the matrix A. That's why we are calling it as trivial solution. And the non-trivial solution for this equation is nothing but determinant of a minus lambda is equal to 0.
Okay. Yeah, Ramu. Here one input to all of you is see we just now we saw some data points and the matrix and everything, right? In the one of the figure you have shown, like what you are Ram shown. So in that, how many unique vectors are there, right? If we have to find, there might be multiple number of unique vectors. You don't know, right? When you given the matrix data points like that, so there is a method to find the how many vectors are there in that. So these unique vectors are having the, there is a way of finding it. This is one of the method of doing it, eigenvalues and eigenvectors. Okay, so that's where this actually, if you think about little bit more about the formula, how it is formulated, right? If you are interested in mathematics and all, you can go. But the thing is that even if you don't also, you can just go to the item like, okay, generally unique vectors. How many vectors are there? First you understood, right? How vectors are arrived and on top of it, how many vectors you need to pick up. So these things would come by doing this kind of math. Finding the how many vectors are there, not there, and all, just like it won't come. There must be some method involved, right? So this is one of the method. Okay. Okay, Ram, go ahead.
Okay. Okay. Then the non-trivial solution occurs when determinant a minus lambda is equal to 0. From this, like a minus lambda I, determinant of a minus lambda I, we will get a equation. When we are solving that equation, we will get the values of lambda, different values of lambda, and for each value of lambda, we can find out the each eigenvector. So as Krishna said, like unique vectors can be found if you know the lambda. So if you know the lambdas, then we can go for the finding of eigenvectors. So with these examples, we can see how to find the eigenvalue first. Find the eigenvalue of a, that is find lambda such that determinant of a minus lambda I is equal to 0. And he has given a is a matrix of second order 1, 4, 2, 3. And we can find out like a minus lambda I means we have, as I say, as we are discussing here from earlier, I is an identity matrix and A is 1, 4, 2, 3, which is given. So with the help of these two, we can go for, this is a scalar, as we have discussed in the eigenvalues and eigenvectors, that lambda is a scalar and we can multiply with each element in the identity matrix. So we know that only in identity matrix, the diagonal elements are 1 other than are 0. So, and the minus of matrices is nothing but in the normal multiplication where each element will subtract from each other, like 1 minus lambda and 4 minus 0 and 2 minus 0 and 3 minus lambda. So with this, we can arrive at a situation like a minus lambda is equal to nothing but this matrix. So we know that we have seen a 3 by 3 matrix determinant. Now we can see here the determinant of a second order matrix. Like we need to multiply with the diagonal element first, that is 1 minus lambda into 3 minus lambda and minus 4 into 2. For this element into this element represents the like determinant of this matrix. So 1 minus lambda into 3 minus lambda minus 8. So lambda square minus 4 lambda minus 5. So we have come across a quadratic equation, and we know that the determinant a minus lambda I should be equal to 0. Then only we will get the lambda values. Otherwise, we will not get a solution. So this quadratic equation must be equal to 0 if we wanted to get the, as we have discussed in this, like the non-trivial solution occurs only when determinant a minus lambda is equal to 0. So we need to equate it with 0 and we will get lambda is equal to -1 and 5. So we have two eigenvalues for this vector -1 and -1 and 5. So for the with the help of lambda value, we can get like two eigenvectors for -1. For -1 we can get a eigenvector, and 5 also we can get another eigenvector. We will see in the further examples. Like here we have like find x bar. X bar is nothing but the notation of a vector such that a x bar is equal to 5x bar, where a is 1/4 the same example what we have discussed in the previous problem. So here lambda we will get like -1 and 5. So here in this example, he has asked, he only given that a x bar is equal to 5x bar. So he has given that lambda is equal to 5. So he has asked us to find the eigenvector. So a x bar is equal to lambda x bar. We know that a minus lambda is into x bar is equal to 0. Therefore, we need to solve the equation a minus lambda I x bar is equal to 0 for x bar when lambda is equal to 5. As we have discussed earlier, x bar should not be equal to 0 because it leads to a non-trivial trivial solution. Trivial solution means nothing but it leads to nothing. Trivial solution. So we cannot equate x bar is equal to 0. Then a minus 5i should be equal to 1, 4, 2, 3 minus 5 into identity matrix -4, 2 and 0. To solve a minus 5i into x bar is equal to 0, we form the augmented matrix and put it into reduced echelon form. So -4, 4 and -2, and this is 0, 0. We have taken this 0 vector here, and we are referring it to 1, -1, 0 and 0. So x1 is equal to x2 and x2 is 3. So here we can now have we have infinite solutions to the equation ax bar is equal to 5x bar. Any non-zero scalar multiple of the vector like 1, 1 is a solution. So we can do a few examples to confirm this. So as Sri Krishna said, like we can have any number of vectors with a unique lambda also. So we can see like 1, 4, 2, 3 into this is a scalar. This is the eigenvector 2, 2 is equal to 10, 10. So which can be written as 5 into 2 by 2. So even 7 also 7, we can represent like 35 into 35 and 7 by 5 into 7 by 7. So here whatever x bar we are taking here, we are getting lambda into x bar the same thing. If we are taking here eigenvector as 7 by 7, then also we are getting here x bar as 7 by 7. So this can lead to like a lot of eigenvectors for a single lambda value. So calculating the eigenvectors, eigenvalues. So we have seen that. So expand the determinant of a minus lambda is equal to 0 for a 2 by 2 matrix. Then we can have these things. We can calculate the here also same thing. Lambda square minus lambda a11 a11 plus a22 plus, and this is c, something like ab square plus ax square plus bx plus c is equal to 0. So we can get a roots for this, nothing but lambda is equal to b plus or minus square root of b square minus 4 ac. So here a is 1 and c is a11, a22 and minus a12 and a21. We know that for any quadratic equation, second order quadratic equation, the solution is here we have like two solutions, that is a b. Actually this is it represents b total, this represents b plus or minus square root of b square by 4ac. So this characteristic equation can be used to solve for x. So here we have got eigenvalues. Example, the same thing what we have discussed earlier, 1, 2, 2, 4. With the help of this, we are getting lambda square minus 1 plus 4 lambda, and we are getting lambda is equal to 0 and lambda is equal to 5. So for lambda is equal to 0, we can find out what is the eigenvector like xy. So here we can see we have like two equations, 1x plus 2y is equal to 0 and 2x plus 4y is equal to 0. So with this, what we can get means like if you're substituting this 2 comma 1, this is nothing but a vector, and if here 2 represents x component and minus 1 represents y component, as we have said. So when we are substituting this, or even if we do not know this also, with the help of this equation, we can say that 1 into 2 plus 2 into 1 or 2 into minus 1. This, here we have like plus. Then if you are multiplying it with minus 1, it will be like 0. So 2 comma minus 1 will be a solution for this. And for the same thing for this also, 2x plus 4y, same thing here also, like 2 and minus 1, the same solution. So lambda is equal to 0. For this, we have x vector as 2 comma minus 1. For lambda is equal to 5, we have, by solving these equations, we will get x is equal to 1. X component is 1 and the y component is 2. So what is characteristic polynomial means nothing but whatever we are getting like lambda square lambda square plus some b lambda plus c is equal to 0. That is called as characteristic polynomial. Let A be an n by n matrix. The characteristic polynomial of A is the nth degree polynomial. That is c of lambda is equal to determinant of A minus lambda I. So here nothing but a quadratic equation if we will get if the matrix order is 2 by 2. So here you can see if it is 2 by 2, we will get second degree polynomial. So second degree polynomial is nothing but a quadratic equation. If it is a third order matrix, then we will get third degree polynomial, that is cubic polynomial, cubic equation. Our definition just states what the characteristic polynomial is. We know from our work so far why we care for this. Okay, n by n matrix A are the eigenvalues. So finding eigenvalues and eigenvectors, let A be an n by n matrix. To find the eigenvalues of x, we are computing. So the same thing here. Steps we have different steps. The same thing. So these are the different examples for solving for getting eigenvalues and eigenvectors. So this I have kept for reference purpose. If you have any doubts, like you can go through these different examples. So the main important is like we need to remember like what are the actually properties of eigenvalues and eigenvectors. Like we have like, since our matrix is a triangular, in this case, the determinant is easy to compute. It is just the product of the diagonal element. So if anytime if you are having like a triangular matrices, like if the upper triangular, whether it is the upper triangular matrix or the lower triangular matrix, then the product of the diagonal elements is nothing but our polynomial, like characteristic polynomial. So we'll get from this equation, we are getting this third degree equation where we can directly get lambda is equal to 1, lambda is equal to 4, and lambda is equal to 6. So that is one of the property of the eigenvalues and eigenvectors with the help within these upper triangular matrix or lower triangular matrix. Triangular matrix is there, then we can say that the product of the diagonal elements is nothing but the characteristic polynomial. The eigenvectors and eigenvalues of A and A inverse. So if lambda is an eigenvalue of A, then 1 by lambda is an eigenvalue of A inverse. The corresponding eigenvectors are the same. So why is this case means we have like derived here. A x bar is equal to lambda x bar, and A inverse into A x bar is equal to A inverse into lambda x bar. So x bar is nothing but lambda into A inverse x bar. 1 by lambda into x bar is equal to A inverse into x bar. So what we are arrived at a situation like A inverse x bar is equal to 1 by lambda x bar. So here 1 by lambda whole represents what? Eigenvalue, and this x bar represents eigenvector. So for a inverse matrix, what we are getting? We are getting 1 by lambda eigenvalue. So that is one of the property of the eigenvalues and eigenvectors, where if lambda is an eigenvalue of A, then 1 by lambda is an eigenvalue of A inverse is the property we need to remember here. So here nothing but A, the eigenvalues of A and A transpose are the same, but eigenvectors are different. So whenever we are coming across like A and A transpose, we have like eigenvalues will be same, but eigenvectors will be different. This is also one of the property of eigenvector and eigenvalues. So these are the some of the properties of eigenvalues and eigenvectors. As we have, like if A is a triangular, then the diagonal elements of A are the eigenvalues of A, and if lambda is an eigenvalue of A with the eigenvector x bar, then 1 by lambda is the eigenvalue of A inverse, and if lambda is an eigenvalue of A, then lambda is an eigenvalue of A transpose. The sum of eigenvalues of A is equal to like triangular A, not triangular, trace of A. Trace of A is nothing but the addition of all the lambdas, that is the trace of A, or even we can calculate with the help of diagonal elements. Like if you are adding all the diagonal elements of a matrix, then that is called as trace of a matrix. If you are adding all the diagonals of a matrix, then that is called as trace of A. The product of the eigenvalues of A is equal to the determinant of A. The determinant is nothing but A. So this is regarding invertible matrix is nothing but whenever it has got A inverse or inverse matrix, then we call it as invertible matrix. So this is regarding the eigenvalues and eigenvectors. And next we have like next we have like actually variance and covariance. Okay, let me share my screen. Is my screen visible like variance? Can somebody say?
Yes, Ram.
Okay, thank you.
So, Ram, I think it is again going to close this in sometime, right?
Within 4 minutes, like, something like it will close.
Yeah. We'll continue the next session, the SVD stuff tomorrow.
Okay.
And from now onwards, I think it's already most of the people already.